This is group lesson number 5 that we're going to go over with you. I'm Steele Rosello.
I'm Valerie Wendell.
Sorry the lighting is so terrible. We just can't figure it out. Anyways, we're going to... Oh, it's really bad actually. Alright, well, whatever. So we're just going to go through the first problem and kind of get a little bit more details. 2, 3, and 4, we're just kind of give you the answers because it's the same basic idea, and then I'll rewrite number 5 for us here at the end, and we'll go through the steps for that. So for number 1, we're doing the trihybrid cross. So for question number 1, it wanted us to find the parent arrangement on that. Let's see here. So it says determine the allele arrangement in the heterozygous parent. So the allele arrangement in the heterozygous parent is just the, you take the 2 most numerous of the offspring phenotypes and you just lay those out according to each one. So you can have them flipped or whatever, but that's the way that we have them here. So you have the little a, capital RG, little mg, capital A, little rg, capital mg for the genotypes that we have put on there. So for B, determine the gene order for these 3 linked genes. So to do that, we basically just followed the steps. So for this one, you need to take the least numerous offspring and write out their, so this one right here is just the least numerous, just written out. And then what you want to do is you switch the middle allele for each of them. So here we have RG in the middle, here we have A, and here we have MG. So you basically just arrange those around that, that center allele because we're trying to determine the gene order that matches the most numerous phenotype that we're seeing in the experiment. So I want to just, when you're going through these, you basically just take the top left, the bottom center, and the top right, and that indicates one phenotype, and the other phenotype is your bottom left, top center, bottom right. And so as you're going along doing those, you're basically seeing which one of those matches the actual phenotypes expressed of the most numerous. And so when you do that for the 3 different options, and these can be MG over here, RG over here, it doesn't matter as long as the center one is changing. But this one right here matches the phenotypes that we have, so we decided that this one was what we're looking for when we determine the gene order. So I guess the gene order is A is when you have A in the middle, and you have RG on the left or right and MG on the left or right. Okay. So for C, we're constructing a linkage map showing the map distances between the 3 genes. So there's a few little steps you need to take before you just can draw out the map. And so what you need to determine are the single crossovers from RG to A and the double crossovers, which are going to be your 2 least numerous. And also you need to do that same thing for A to your MG. So when we put those through and match them with the phenotypes and the numbers, you have 1 and 1 of the least numerous, and then it falls into the 16 and the 18 category that you have listed on your group work there. And then for the A to the MG, similarly you have the 1 and the 1, and then 13 and 12. So when you plug it into the calculation on the instructor notes that was given, basically you're going to take the sum of those numbers and divide it by your total progeny. So the total number that we have captured in the experiment. So when you do that for RG to A, we got 0.175 or 17.5 MUs. And likewise on this one, when you do the calculations, you get 0.131 or 13.1 MUs. And then once that's determined, then you can draw out your linkage map, which is just right here. So you have your RG 17.5 MUs to your A, and then from your A, 13.1 MUs to your MG. Okay. That's linkage map right here for that. So for D, we were trying to calculate the interference. So when you're calculating the interference, what you need to do is take the frequency. I actually wrote this wrong right here. So this should be your 0.175 times your 0.131, and that will get you your frequency of each of these happening. So this is a product rule thing because the chances that they're both happening, it's not an or, it's not this or that, they both happen. And so you take your total progeny times that frequency, and that will give you what your estimated double crossover number of progeny should be, which in this case is 4.7. So when you're calculating interference, you have your interference equation that's given to us in the instructor notes. So you have I equals 1 minus C, and C is your observed over your expressed phenotypes. So if we just basically plug that in, I equals 1 minus 2, because we have the 1 plus 1 as the least frequent, 2 divided by 4.7, and you just plug that through, you end up getting I equals 0.575. So that's your interference, and then when you multiply that to a percentage to calculate how many of the DCOs did not occur, you get 57.5% of those not occurring. Okay, so that's how you answer number 1.
All right. And then just like Steele said, you solve 2, 3, and 4 exactly the same way. So since we already explained how to do it, I'm just going to go through and tell you what we got. So for 2A, we got, and so just so you know, for me, what I did, when there's a plus, that represents that it's the wild type. So for A, we got SC plus, SV, and then on the bottom, SC plus, or S plus, and V plus. And then for B, or I guess the gene order, we got S, SC, V. And then the distance between S and C is 33 MU, and the distance between SC and V is 10 MU. Then for D, we got 27%. For number 3, we got G plus C S plus over G C plus S, and then for the order, we got SCG or CGS, whichever one. And then for C, the distance between S and G is 1.9 MU. And the distance between G and C is 7.5 MU. And then for D, we got negative 1,233.33%. And then for number 4, for A, we got AN plus BRF on top and AN BR plus F plus on the bottom. And then the order, we have BRF AN or AN F BR, whichever way you put it. As long as F's in the middle, that's all that matters. And then for C, the distance between BR and F is 5.1 MU, and the distance between F and AN is 19 MU. And for, I think I read decimal. Oh, no, I did. Sorry. Okay, and then for D, it's 0.969%. And so now we're going to go through 5, because I don't know, it was a little bit trickier for us, and so we wanted to explain how we got it, just so that everybody's just kind of on the same note as. So do you want me to do?
We can draw that out. So we'll draw.
And pictures help.
That's how we figured this out. Yeah, we were a little confused at first, and then we drew it out, and it kind of made more sense.
A lot, yeah.
All right, and you just want to fill in the letters there.
Okay. Alright,
So we were having troubles. I mean, this one was kind of tricky to figure out at first. We just kind of had to read it out loud to each other and draw it out, and basically following the steps of meiosis 1 and 2 to get your 4 gametes, and kind of just thinking that through and drawing it out. So I guess I'll let you do A and B.
Okay. Let's,
and then I'll
let me just check on this.
so yeah, they have
Okay, so, alright, A and A are on separate, okay, so A and A, B and B. Okay, so for A, it says suppose a cell has genotype capital A, lowercase a, capital B, lowercase b, assuming that capital A and lowercase a are on separate homologous chromosomes, then B, so A's and B's are together, sorry, read that wrong. Okay, so the capital A, lowercase a are on separate homologous chromosomes, then capital B, lowercase b. What are the genotypes of the gametes produced by the cell? What is the frequency of each of these gametes? And so when you go through and you cross these, let's see, here it would be A, B, and AB, right? And
yes,
yeah.
yeah.
Okay. A and B. So when you go through meiosis 1, you'll get these, and then when you combine, when you combine them, you'll get A, and then B, B. Okay. So when you go through meiosis 2, again, then you will end up getting all 4 capital A, capital B, capital A, lowercase b, lowercase a, capital B, lowercase a, lowercase b.
Yeah. I think this one actually has all. Shouldn't these have 4 because then
Do they have 4? Oh, and they split into 2, so then these would have. Oh, okay.
yes.
Sorry. Okay.
That's what
That's how they will look, and then when they split, yeah. Sorry. Then you'll get those 4 genotypes, and then it will be the frequency will end up being a 1 to 1 to 1 to 1 ratio as you get each of those. Then for B, it says suppose the cell has a genotype A, capital A, lowercase a, capital B, lowercase b. In this case, A is linked to, or capital A is linked to capital B, and lowercase a is linked to lowercase b. So it'll end up being that. And then it says, for this problem, assume that crossing over does not occur. So if crossing over doesn't occur, these won't mix, so you'll end up just having
too large. Yeah, you have AABB all caps, and then AABB all lowercase.
And so then the only options that you can get from this one is capital A, capital B, capital A, capital B. And from this one, you'll only get lowercase a, lowercase b, lowercase a, lowercase b. And so in that case, you would end up getting a 2-to-2 ratio instead of a 1-to-1 to 1-to-1 rate frequency, I suppose.
Okay.
Or, yeah, 1-to-1 to 0-to-0.
Yeah. All right. So for C, we actually got the same results for C that we had for B. So we got the genotypes possible were A, B, and caps or dominant and recessive for each, and so the ratios were the same again. So A is linked to B, and A, dominant linked to dominant, and recessive linked to recessive. So just like you see here, what are the genotypes of the gametes produced if the cells if crossing over occurs between the AA alleles and the BB alleles? Okay, so we got the same results for that one. So for D, this one was a little different. So it says, referring to the situation in part C, suppose the map distance between the AA alleles and BB alleles is identical for both, so both 7.8. What's the frequency of each of the gametes produced by the cell described in part C? So it's kind of like calculating the interference, but you don't have to go all the way to the interference equation that we had before. You just have to do frequency. So basically you take 7.8 MUs divided by 100 times 7.8 divided by 100, or squared, however you want to do that, and we got 0.00608, And so your frequency, you just multiply that number by 100. So the frequency of gametes produced should be 0.608%. So don't need to go any further than that because then you're getting into interference stuff. So that's what we got.
Thanks for watching.
Yeah, see you next week.